So let's say we're interested in some matrix A. We're limiting ourselves to the 2 by 2 case, although a lot of this does generalize. So a 2 by 2 matrix with complex eigenvalues. And we understand the behavior of these special 2 by 2 matrices with complex eigenvalues, multiplying by a matrix that looks like this, rotates the vector, then scales it. Rather than approach this in generality, let's look at a specific example. This matrix A has complex eigenvalues, but it is certainly not of this form. In particular, here are the eigenvalues, and I always talk about complex eigenvalues plural, because if you have one complex eigenvalue, you have two. Complex roots appear in conjugate pairs. Well, so do complex eigenvectors. The eigenvectors are corresponding, to these eigenvalues are complex. And as I say, they appear in conjugate pairs. In general, finding complex eigenvectors is a mess. Your calculator can't do it for you because it doesn't really work well with complex numbers, and doing the requisite Gauss-Jordan elimination by hand is a bit of a nightmare. This example comes from the textbook, but if I ran into it in the wild, I would use Wolfram Alpha or some other kind of computer assistance. So we're now going to perform a sort of pseudo-diagonalization. So remember, when you diagonalize, you rewrite your matrix so that it looks like this, where D is diagonal. We're going to do something very similar, except instead of a diagonal matrix, we're going to have a matrix like this, a matrix in its special form whose behavior we understand. And the way we're going to do that is to take the real part of these, I should say, eigenvectors, and take the imaginary part and form a matrix like so. In this particular case, our real part is this vector, and our imaginary part is that vector. And if we multiply P inverse times A times P, we get one of these matrices in its special form. That's a theorem. We do not prove it. I simply say that it's true. Then we multiply on the left by P and on the right by P inverse. And A is indeed similar to one of these special matrices, just as we promised. We'll get into the implications of that in the next video.